Good. My name's Stephen Belcher. I'm the Chief Scientist at the UK Met Office. So the Met Office and the University of Oxford co-host the Houghton Memorial Lecture. And we think this is the 4th lecture. So we've had a very distinguished programme of speakers, and Karen will add to that distinction this afternoon. So just let me say a couple of words about John Houghton. I don't know how many of you are aware of him or knew him. So John was a very distinguished academic here at Oxford, and I think Tim might pick that up in just a minute, and then moved in the 1980s to become Director General, what we now call Chief Executive of the Met Office. And he was one of those great men who kind of did some really big things. So there was a famous storm in 1987. See how Met Office I've become? I used to be an academic. So there's a famous storm in 1987 when I was a student, and I slept right through it, but it destroyed many trees. And the forecast was not the best one that the Met Office has ever produced. Let me just leave it at that. But John did see the opportunity to get a new supercomputer, a more powerful supercomputer for the Met Office. And as a result of that increased supercompute, the forecast did improve. Something else that John was able to do during his time in the late 90s, when Margaret Thatcher was Prime Minister, was to brief her on the concept of climate change. And famously, because she was a chemist by background, she got it really quickly. And so one of the outcomes of this discussion was that Margaret Thatcher sponsored the establishment of the Met Office Hadley Centre, which is still going today, started in 1990. And of course, many collaborative projects with folk here at Oxford, so a real joint success. And then John not only did that, but then he helped to co-found the Intergovernmental Panel on Climate Change, the IPCC, which you'll all know provides the scientific evidence base for climate change. On top of that, he was a really amazing guy. So I'm sorry, David, I'm going to tell this story once again, and I'll keep it brief. Just after I joined the Met Office, I was the director of the Hadley Centre, and John Houghton asked if he could come and visit to talk about a revision to his book. So I said, delighted, come on down. On that day, we also had a group from Department for Environment, Food and Rural Affairs coming. So yep, come on down. And David and possibly Helen were coming from Oxford to talk about oceanography, all on the same day. It then poured absolutely biblical amounts of rain. David and Helen didn't quite make it because it's quite a long way from here to Exeter and the trains weren't running. The DEFRA team didn't quite make it because the trains weren't running. John, however, from Oxford, he was well into his 70s, late 70s by this stage, got to Bristol, and I think he got a taxi down and, you know, some miracle, pitched up at the front door of the Met Office. And I said, how did you do this? He said, well, I didn't want to waste a whole day. So he was a great man in many ways and a very sort of personable character. And it's delightful that we can welcome some of his family to listen in on this lecture. So welcome from the Met Office. Thank you to Karen for accepting the invitation. And I think, Tim, you're going to give an introduction from an Oxford perspective.
Great, yes, thank you, Stephen. Really nice to see everybody here. Oxford and the Met Office obviously have a long history, and so it's great to do this event in tandem. We've been kind of alternating hosting this from year to year. So John Houghton, before he moved to the Met Office, worked here in what is now called AOPP, where I think lots of you are. At the time it was called atmospheric physics. He worked a lot on kind of atmospheric radiation, taking measurements, something which I think will resonate in Karen's talk today. And he really took atmospheric physics here into the space age then, with his work on kind of really pioneering satellite observations. So as Stephen said, it's great to have the Houghton Lecture every year and to welcome some of the Houghton family online today. So nice to have you here again. It's especially nice to have Karen here. Karen kindly accepted our invitation to come and talk to us. Karen is a real kind of pioneer of observational oceanography, in particular using kind of autonomous systems to measure the ocean, which I think we're going to hear a bit about today. And I know there are some people from engineering here today as well in Oxford who work on autonomous systems today. So I did a little bit of homework. So Karen did her physics undergrad. It's nice we're in a physics department. So Karen did a physics undergrad in Bristol and then moved to Southampton to do a PhD with Neil Wells, I think, which is great. And then Karen worked in Bangor, I think, for a bit in UEA. Karen is the first female professor of oceanography in the UK, which I think we should maybe applaud. And according to Wikipedia, Karen has trained more than 40 PhD students, which is really incredible. So, so well done. Very, very valuable training. So we're going to hear a lot about Karen's observational work. Karen's been chief scientist on several kind of ocean cruises. Karen is a fellow of the American Geophysical Union. She's a fellow of the Royal Society, she's OBE. And I think the best thing, I don't know how you feel, but there is apparently a glacier in Antarctica, which is named after Karen. There is a Heywood glacier, which I think is really amazing. So it's really lovely to hear Karen, have you here. Thank you for talking to us. And yeah, please take the floor.
So thank you. It's a huge honor to be invited to give the Houghton Lecture here. So thank you for inviting me. And it's been lovely today to meet some of the PhD students. I have indeed had more than 40 PhD students because I love the future of science. I like interacting with the young people. So my aims today, I suppose, are to give a little bit of a flavor for some of the things that I'm doing and which I think you as the new generation of scientists can also be involved in. So I have up on the list a list of the people who've contributed to this. So many of these are my students and postdocs. So I can't take credit for much of what I'm going to show you. But it's all thanks to them and many others who contributed to the observations that I'm going to show. So I chose to talk about oceans and ice shelves because I'm really interested in ice shelves. And I'm going to start off, this is my outline, I'm going to start off by saying, why should we care about ice shelves? So an awfully long way away. And then I'm going to talk a little bit about how can we observe ice shelves and in particular the ocean's interaction with ice shelves, with the ultimate goal of being able to predict and forecast what's going to happen to those ice shelves in future. And there are 3 ice shelves that I'm going to focus on, 2 of them in the Amundsen Sea, Thwaites and Dotson, and 1 in the Ross Sea, the Ross ice shelf. So, I've kind of got a little bit of a mixture of different ways of observing ice shelves. So the first question is, why do we care about ice shelves? Well, essentially it's sea level rise. We all know about sea level rise. It's affecting lives and livelihoods around the world. And it all goes back to Sir John Houghton, actually, and earlier. And I looked up I wanted to put a figure on here of what the very first prediction of sea level rise was in the IPCC report in 1990-1992, which Sir John was the co-chair of that working group. And I think it must have been quite daunting back in 1990. I'm old enough to remember 1990. And it must have been quite daunting to be given the task of assessing available scientific information on climate change. It seems obvious to us now, but in those days, it wasn't that obvious that you could put together a summary of what science thought. So it was a huge undertaking. And this figure up in the top left is their predictions, their best estimate, high estimate, and low estimate of the sea level rise. And I should point out that they started it from 1990. That was when they wrote the report. So the 0 is at 1990. But at that time, their low estimate was around about 30 centimeters by the end of this century. Their best estimate was somewhere between 60 and 70 centimeters. And the high estimate was about 110 centimeters by the end of this century. And there is Sir John giving a lecture. I don't know whether it was in this room, but he was giving a lecture on the changes, the climate changes, and the global temperature record. So how does that compare with what we think now? So this is from the most recent IPCC report. This is now sea level relative to 1900. So I've done what I always tell my students not to do, which is change things from one plot to the next. But the message is kind of about the same. So what's the range of our current predictions of sea level rise by the end of the century? Well, the 30 centimeters has gone. So we don't think the low estimate is no longer about 30 centimeters or so, it's more like 50. And the highest estimate on the scenarios that are run is around about a meter. So not that different really from what Sir John and his team came up with all those years ago. But one of the things that has changed over that time is this high impact storyline. And this is the worst case scenario, if you like. It's what would happen if the ice sheets in Greenland and in Antarctica were to become unstable and lose a lot of their ice mass. So nobody's saying this is highly likely to happen, but it's something that we need to explore and investigate. So I've put on the right-hand side, Antarctica contains 90% of the fresh water. If all that were to melt, which it won't, I mean, this is kind of just to give you a feel, if all that Antarctic ice melted, it would be 58 meters. So it's a huge source of fresh water that's locked up in that ice. So this is really why we're interested in understanding Antarctic ice, because it can impact all of us on the planet. But again, this is nothing new, really. Right back in 1978, when most of you probably weren't even born, there was a paper talking about the potential for disaster if the West Antarctic ice sheet were to collapse, to melt, due to CO2 greenhouse gases. And what's interesting about this abstract is it talks about atmospheric CO2 content will double in 50 years, which is around about now. And it's talking about the rapid deglaciation of West Antarctica. And that's a region where I'll focus on for most of my talk today. So West Antarctica, this is the region that we're looking at here. So it's the Antarctic Peninsula and the West Antarctic Peninsula, the Amundsen Sea and the Bellingshausen Sea. And it was termed right back in 1981 as the weak underbelly of the West Antarctic ice sheet in the Amundsen Sea. And the reason for that is that beneath that ice, there is land which is below sea level. So the more that ice melts back, the more water, the ocean water, is able to penetrate inland. And so there's a potential for feedbacks and to lose a lot of ice mass from the ocean underneath. Something perhaps to discuss in the pub in the evening is, should we be doing something to stop the ocean interacting with ice shelves? I'm not going to say much more about this, but there have been calls, and indeed people are investigating and running models to see or to investigate whether we should be building some kind of barrier in front of ice shelves in Antarctica or elsewhere that would be able to depress themselves as icebergs went over them, but would be able to stop that warm water from the ocean getting towards the ice shelves. I'm not going to tell you what I think of this, but you can read some articles. There's a lot of interesting articles online, and some reputable scientists are running models to show what would be the impacts of doing this sort of study. So what do we know about the loss of ice in Antarctica? This is a measurement derived from satellite altimetry, measuring the height of the ice around Antarctica, and it's looking at the rate of change. So anywhere where it's blue, the surface of the ice is increasing. Anywhere where it's red, the ice is losing mass. And the particular area where the highest reds and purples is the Amundsen Sea and the Bellingshausen Sea. So those are typically areas that we've been investigating over the last decade or so, trying to understand why those are melting more rapidly or losing their mass more rapidly. And I should say, because there are lots of meteorologists in the room, of course, not all ice shelves are impacted by the ocean. Some of the ice shelves are very much impacted from surface effects. So the Larsen ice shelf, for example, is being melted from warm winds. Excuse me. But I'm an oceanographer. I'm particularly interested in the ice shelves that are impacted by the ocean. And the reason for that ocean interaction with the ice shelves is shown in this figure, which I really like, which shows the maximum temperature on the continental shelf all the way around Antarctica above the local freezing point. So that's what we're calling the thermal forcing. So in other words, the warm, relatively warm, it's a few degrees above local freezing, water from the open ocean that is penetrating onto the Antarctic continental shelf. And what you can see in this figure is that the areas where the darker turquoise color, there the water is about 4 degrees above freezing. And those are exactly the same places where we've seen the rapid rate of ice mass loss from those ice shelves. So the ocean is implicated in that ice mass loss. So one thing I should say straight away, for those of you who are not ice shelf fans, is that the ice shelf is the bit of the ice sheet which is floating. So the glacier is sliding down Antarctica, and when it meets the ocean, it floats on the surface. So there's a cavity underneath that ice shelf. And these ice shelves buttress the glaciers further upstream. In other words, they're kind of propping them up. If you take that ice shelf away, the ice sheet accelerates faster towards the ocean. And that can lead to more iceberg carving, for example. So this figure shows all the myriad processes that we believe are going on, in particularly the warm ice shelves, so the Amundsen Sea, for example. And here out on the right-hand side, we have the Antarctic circumpolar current, which is essentially, from the point of view of Antarctica, a big source of heat. And that heat can get onto the continental shelf. That's this red current here. And it can flow all the way to the grounding line or grounding zone here, which is the point where that ice shelf comes, it stops being grounded. And then typically the water will flow out and lots of meltwater will be coming out nearer the surface. And I'll come back to that later on. The ice shelf front will carve glaciers, carve icebergs from time to time. And we often get plankton blooms. And if any of you are biogeochemists, there's nutrients brought down with the iceberg, with the ice shelf. And those nutrients or micronutrients like iron and manganese can then fertilize the ocean. So these issues are not just of interest to the physical scientists. So essentially, in the last decade or so, I think everybody has realized the importance of these studying ice shelves. And so one of the things I've really enjoyed about working in this field is it brings together the oceanographers, the glaciologists, meteorologists, people who like shiny yellow toys that I'm going to show you in a minute, ocean modelers. It brings everybody together because everybody can bring their own expertise to this problem. And as I say, work with the biogeochemists as well. So this rather nice figure summarizes all the different ways that we can observe this very complicated and very challenging environment. And I'm going to focus in my talk on a few of these. I'm going to talk a little bit about autonomous underwater vehicles, little yellow vehicles here. And I'm going to also show some results from moorings that are deployed through the ice shelf. I'll also show a little bit of results from ships. And I'm not going to talk about most of these glaciological processes, or instrumentation, even though they're of a lot of interest. So let's start on the first of those examples. And this is an autonomous underwater vehicle owned by the University of Gothenburg that we deployed in 2019 underneath the Thwaites ice shelf. People may remember that the media loves to refer to this as the Doomsday Glacier. I have to say, most of us don't really like that word, but the media, well, it does bring a lot of media attention. So Thwaites is a very large ice shelf and a particularly vulnerable one. My glaciological colleagues are very excited about the fact that bits of it might be breaking up fairly soon. So it's a good example of an ice shelf that we need to study. So we sent the RAN, which is the name of their AUV, underneath the Thwaites ice shelf. Didn't go very far, but it was of great value. And it's the sort of thing, those of you who are engineers, you send something like an AUV like this into a cavity, and it's the first time anybody's ever made measurements inside that cavity. One of the things I love about ocean science is there's still so much to explore, to learn. So what did we find? We looked at the temperature and the salinity of the water underneath the ice shelf, and we compared it with the waters on either side of this ice shelf here. So we were sending the AUV under here. This is Pine Island Bay, the other glaciers upstream. And what we found was there was as much water coming in from the Pine Island region as was coming in from the other trough that was expected to feed Thwaites. So it was kind of being attacked from two sides. And we were able to look at the processes of mixing underneath that glacier ice shelf. So the other thing that we did on that particular mission, and this is particularly for any of you who are earth scientists, was we used the RAN AUV, now not looking at the ice shelf itself, but looking at the seabed where that ice shelf used to be grounded. And what we saw with this really high resolution, because it was a small AUV and it was going just above the seabed, and it mapped the seabed in unbelievable detail. And we saw all of these funny little ribs in the seabed. And we all sat around saying, what on earth could have caused these parallel ribs on the top of this bump? And eventually, Ali Graham, who led this work, he realized that what was probably our hypothesis is that every tide, and the tide here is diurnal, so once a day, the ice shelf is going up and down, and it's landing on this bump. And each day, the glacier is moving a little bit further. The ice shelf is moving a little bit further out. So you get this series of ridges. And by comparing this with the tide model, we were able to see that we can even see the spring neap cycle, the 14-day cycle, in this series of ridges. So equating the distance between these ridges to time, Ali was able to work out how fast that ice was retreating. And it was more than 2 kilometers a year, which is much faster than it's retreating now. Now you could say, well, that's great, isn't it? So it's not as fast as it used to be. We don't know when this was. We don't know when the ice shelf was bumping up and down on the seabed. We don't have any dates for that. But what it does tell us is its potential for much faster grounding line retreat in paleo time. So that could easily happen again. So it's telling us what might happen in the future and certainly has in the past. So my next example is using a hot water drill to make a hole through the ice shelf into the ocean below. It's a lot of work, takes a lot of oil and a lot of time. So you're pumping hot water into the hole, you're gradually making a hole through maybe 300 or 400 meters of ice shelf, and then you're putting your instruments into the water below it. So here's the surface, and the surface is what's shown in the picture. So there's a MET station on the surface. And then we're making measurements through the ice shelf itself, through the ice, and then out into the ocean, which is down here. And that's the observations that I'm going to show you. So we have temperature and salinity and ocean currents in the cavity beneath the ice shelf. So not close to the entry, but quite a long way from the open ocean. And what we found from those measurements was that the current was very much flowing into the ice shelf cavity from Pine Island. It was coming from upstream. And this is the sort of current rows, so it's all going in this direction. And down at the bottom, we've got output of a model that Yoshi ran. And what he's doing is planting tracers into the Pine Island cavity upstream of Thwaites and seeing where they go. And these dots are where our sensors were. And what we're seeing is the connectivity between one ice shelf and the next. It's worth saying that the water that comes out as meltwater is actually warmer than the water around it, because it went in warm and it's coming out a little less warm, but still warmer than the water around it. So then that water is going under the next ice shelf. So each one impacts the next. And from the time series, one of the nice things about putting a mooring down is that you don't just get a snapshot. You haven't got one measurement, you've got several years. And we had several years of measurements beneath Thwaites. And what we found is that there were differences from one year to the next. So in the 2019-20 summer, the water, there wasn't much sea ice around, and that enables the wind stress curl to drive a gyre, quite a large gyre. Whereas a year later, in summer 2020 to 2021, whole area was covered in sea ice. So that leads to much less of a gyre in front of or between Thwaites and Pine Island. And this meant that because of that gyre, or what we saw in the observations, was that in the year when there was less sea ice, we were seeing colder water in the cavity, less meltwater. And in the second year, we were seeing warmer water in the cavity, more meltwater. And our hypothesis for that is to do with that gyre, the spinning up of that gyre and the steepening of the density surfaces, the isopycnals around that gyre. So if there's a steep gradient here, then you can get water from here going underneath Thwaites and more easily. And this is consistent with the observations that we were making. This is a piece of work that I wasn't involved in at all, but which I thought it was kind of cool to tell you about. So this is work done by Brittany Schmidt and Pete Davis at Bass. Brittany Schmidt is in the US, and she has an amazing tethered autonomous underwater vehicle. So one I showed you earlier, the RAN, that's completely autonomous. You send it away from the ship and it makes its own decisions about where to go. This one, I don't know how clearly you can see, but there's an umbilical. So it's connected to the ship, or in this case, to the ice camp. And what they did was put ice fin through holes in the ice shelf right close to the grounding line of Thwaites. Brittany's actually developed this for deploying on places like Europa. So the idea is that it would all essentially be automated. It would land on an icy planet and be deployed down holes. So she's trying it out on Antarctica first. And these are the results that they got, which I think are really exciting. So she's right up near the, sorry, ooh, what happened there? She's right up near the grounding line. So the bit where the ice shelf and the seabed come together, so really narrow, not sort of place you'd want to send an autonomous vehicle down, but you can send one of these tethered ones. And these are the observations that they gained. And they found that up at the surface, there was much cooler water than down below. And that water, the warm water melting the ice shelf, and then up above was kind of insulating the bit of that ice shelf up there. So these are really exciting techniques that can be used for this sort of study. How am I doing for time? Okay, so now I wanted to say a little bit about what can we deduce about the oceans and ice shelves without actually going underneath the ice shelf. Isn't it a lot cheaper, a lot easier to make measurements at the front of an ice shelf and not go underneath? You can certainly learn a lot from that. And this is an example of what you can learn. So I'm moving now to Dotson Ice Shelf. Dotson is next door, so you've got Pine Island, the furthest east one in the Amazon Sea. Then you've got Thwaites, and then you've got Dotson. So they're all in a row. They're all subject to similar forcing, ocean forcing, warm water. So we were meant to go to Thwaites, but we couldn't because there was too much sea ice. But Dotson is a really nice, much easier ice shelf to study anyway. It has a nice front here, and we were able to do some CTDs, in other words, ship-based measurements, profiles of temperature and salinity all the way along the front of Dotson, and we measured the flow. So the pink arrows, if you can see them, are the currents into the Dotson ice shelf and out of the Dotson ice shelf. So the inflow is in the east and the outflow is in the west. It usually is. That's Coriolis force for you. And on the right-hand side, we have sections of temperature. So now depth is on the y-axis, and this is distance from west to east along that section. So you can see this warm water at depth. So below 500 meters, that's the source of the heat that's coming in under the ice shelf. The next panel down is the velocity. So the red colors here on the right-hand side is a current coming towards us, going into the ice shelf and ice shelf cavity. And on the left-hand side, on the west, further up in the water column, because it's been made more buoyant, is the meltwater-rich outflow from underneath the ice shelf. And what we've done in the bottom right panel is to add up the total amount of heat that is going underneath, so the net amount of heat going into that ice shelf cavity. And if you do that calculation all the way along that section along the front, you come up with the amount of heat that would be about 20 gigatons per year. And that's fairly typical to the last recent, so there's been a few estimates over recent decades, and 20 gigatons per year is not one of the highest numbers, and it's not one of the lowest, but it suggests that Dotson at least is not running away in terms of its ice shelf melting. So the other nice yellow toy that we deployed on the same campaign as the section is auto-sub long range. So this is the UK's version of the Gothenburg RAN AUV, colloquially known as Boatim boat face. And it has at the front of it a turbulence sensor. So in 2022, we sent auto-sub long range underneath the Dotson ice shelf. So here at the top is the same section that we've just been looking at, the ship-based measurements. And here in the sort of trident pattern are the missions that auto-sub long range did into that Dotson cavity. So the longest section is about 45 kilometers. I'll focus mostly on the eastern one, that's the inflow. And this is a bit of a slightly complicated figure, so I'll talk you through it. So here is, on the left-hand side, this is where we're sending the auto-sub long range into the cavity. And it turns around here, where the vertical line is, and then it's coming back out. So at the top, we have the ice shelf, the base of the ice shelf. And at the bottom, in gray, we've got the seabed bathymetry. And then it's probably too small to see, but there's a very thin black line there. And that is where the auto-sub long range was. So it was programmed to go in and be 100 meters above the seabed. So it was navigating relative to the seabed, and it just followed the bumps in the bathymetry up and down. And then the blue colors just above and below that is the current measured by the auto-sub long range. And essentially all you need to take from that is it's all blue, it's all water on this section, at least this is the eastern section. It's all going into the cavity. And it's not going very fast. This is in meters a second, so 0.1 meters a second, 10 centimeters max, and probably less. And there isn't very much shear, it doesn't vary very much above and below the sub. The top time series, so it's now offset, so this is not the depth that it actually is, it's just offset from the others. The top one, the sort of orangey red colors, is the temperature. And here, what I want you to take it away is that the temperatures are above zero. The freezing point is about minus 1.8. So there's plenty of heat there going into the cavity that would be available for melting. The green line in the middle, this was the novel measurements really, because it was measurements of the turbulent mixing in that cavity. And what we take away from here is that the mixing is round about 10 to the minus 9-ish watts per kilogram. That's low. So it's not very turbulent. In some ways, we were quite disappointed because mixing, people always want lots of mixing because it's more exciting. But in terms of the ocean, what it's telling us is that water isn't mixing very much as it's going into the cavity. That means that that heat will still be there 100 kilometers into the cavity when it gets to the grounding line. So it's not going to lose its heat really quickly. So here are a couple of maps of the same data. We've now got both sections. The left-hand panel are the sub-long range trips into the cavity, colored by temperature, and the arrows are the current. And on the right-hand panel, that's covered by the amount of mixing. And what I want you to take away from here is it's this inflow on the eastern side that is the warmest and also has the higher values of turbulence, even though they're not that high. So on the same mission, we also deployed RAN. So we had sub-long range at the bottom, looking down at the inflow. And then we also had the Gothenburg AUV, and it was looking up at the underside of the ice shelf. So I showed earlier the swath bathymetry of the seabed. This is using exactly the same technologies, a multi-beam, and it's looking up at what does the ice shelf base look like. And classic wisdom is that you look at an ice shelf from a satellite image and it's all quite smooth. So everybody feels that it must be smooth underneath as well. And surely there's all that mixing going on. So it'll all be nice and smoothed out. And what we saw from RAN just turned that on its head. What we saw were these amazing patterns, sort of teardrops and crevasses and swirly patterns. And we had a fascinating workshop where everybody sat down and threw around ideas about what could be causing all of these patterns. And this is a sort of sketch of those phenomena. And I'm going to focus particularly on the one, so I should say. So we're now looking the other way around. We're looking into the cavity. So here's the deep inflow on the left-hand side going in. And remember that the measurements made by RAN are just underneath, so they're up here. And then the outflow was coming out where the AUV was surveying here. And the ones that I think as physical oceanographers we got most excited by were these teardrops. And they were all curving the same way. And our hypothesis, we can't prove it, but our hypothesis is that this is caused by an Ekman layer in these small teardrops underneath the base of the ice shelf. So all of this wealth of data really changed our understanding of what was happening on the base of that ice shelf. It was much more dynamic and much more heterogeneous than we had expected. So the last example that I'm going to show you is ocean gliders. Some of you will know I'm an ocean glider fan. And these are a much smaller, much more environmentally friendly, much easier to lose platform for making observations, particularly in hazardous locations. And I'm moving now to a cold water ice shelf. So this is the Ross Sea. So it doesn't have that warm water melting from underneath. So in 2022, we deployed this glider from the edge of the ice shelf into this open water polynya in the Ross Sea. And we put the glider in fact, we put 3 of them in. One of them never came back, and one of them disappeared for 3 days. We were very worried. I was worrying about what I was going to tell my head of department. But after 3 days, that glider came back, and we were absolutely thrilled with the data set that it came back with. And it had been underneath the Ross ice shelf. And this is a time series of what it had seen. Of course, we don't know where it went, and that's the real frustration. We don't know how far in it went. But we still got some really interesting observations right underneath the ice shelf. So what we found was that the water underneath the ice shelf was actually surprisingly warm and had the same properties as the water just outside the ice shelf, even though the ice shelf was about 100 meters down. And we believe that that is solar warmed, fresh surface water from outside that has just followed the density surfaces, the isopycnals, underneath the ice shelf. And that was supported by the biogeochemical measurements. So the chlorophyll, for example, was quite high. So, and you wouldn't be able to get that sort of growth of phytoplankton underneath an ice shelf. So it must have come in from outside. Same with the oxygen. So what we were seeing was water being pushed underneath that ice shelf. And it's our friend Ekman again. We believe it's forced by the wind and pushed underneath that ice shelf. And of course, this might be important in future because if the sea ice reduces, if the winds were to increase or move poleward, then there might be more of this water going underneath ice shelves and enhancing that melting near the ice shelf front. One of the things, this is the last thing I'm going to talk about, one of the things that I was really excited about was the fact that those gliders went really close to the ice shelf. How else could you get measurements right underneath an ice shelf? If you drill a hole, you've perturbed the environment. If you send an AUV in, there's no way you want that AUV to be in the top few meters right underneath the ice shelf. Our glider, not intentionally, our glider was going up and down, and every time it came up, it was saying, I want to get to the surface. I want to transmit my data back. But it couldn't because the ice shelf was in the way. So it was bumping along in that layer just immediately underneath the ice shelf. So what we did was we gathered up all of the data in that warm area where the warm water was underneath, relatively warm, underneath the ice shelf. And here the purple is the area where the water underneath was cold, presumably further in, though we don't know. And we've done an average of those two. So that's what's shown here. So the purple line is the cold regime. So in that area, what we found was the mean over all of the profiles from the glider was pretty uniform. So top to bottom, pretty uniform. But the warm regime, and I should point out that we have, this is all relative to the value at 5 meters. So this 0 is, or has had what's at 5 meters subtracted from it. So these temperatures would not be the same. The orange one is actually warmer. But what we see is this exponential decay of temperature as you move towards the base of the ice shelf. And to our knowledge, this is one of the first measurements of what the temperature is like immediately under the ice shelf. And hopefully that's the sort of information that one can feed into models to better understand and be able to parameterize how the ocean and the ice shelf interact. So my penultimate slide is a little bit of the vision for the future. So I think, as people alluded in the introduction to me, I'm very much in favor of autonomous observing systems, partly because they're usually environmentally friendly, they don't perturb what they're going to measure, relatively cheap, and to me, a network of ocean gliders, a network of profiling floats like Argo floats, assuming that they don't all get cancelled by the US president. So a network of these sorts of technologies around Antarctica is what we need to have an observing system, multidisciplinary observing system. And in fact, in 2018, there was an amazing experiment, though they'd never written it up, so it's a bit frustrating, but the group at University of Washington, together with Pierre Dutrieu, who's now at Bath, they did a super experiment where they put sound sources in front of the Dotson ice shelf, and they sent floats and gliders underneath that cavity. And to me, that's the vision of what the future could be for ocean observing. And I also got the picture of the seal with the sensor on its head, because again, that's another way of getting measurements in an inaccessible environment, particularly in wintertime. So, my conclusions of this talk. So, I think we're beginning to understand these processes, but there is hugely more to learn. So those of you who are early career scientists, there's so much potential here for people who want to model or observe or design these new technologies and use them. So I think one of the things that I suppose I hadn't realized before we did all of these observations was how connected all of these ice shelves are. You can study one, but actually you've got to be thinking about how is that water preconditioned by what's happened upstream. We should be looking at ways to see what these ice shelves were like in the past, because that may help us understand the future as well. And measuring the mixing is important because it'll tell you how much of that warm water can get towards the grounding line. The importance of wind, and particularly if we look in terms of climate change, how might these ice shelves change in future? So there's lots still to do. Might not be me doing them, but hopefully it can be you. So thank you for listening.